recurrent neural networks, and we'll be focusing on the so-called simple neural networks. And a lot of people active in the literature now, they prefer the word vanilla neural networks. So I'm using the simple neural network to refer to what other people call vanilla neural networks, which is really the basic structure of recurrent neural networks. In a simple way, cartoon fashion, that what are those mappings? If you view this block, which is a recurrent neural network, is going to take a signal, okay, to another signal. So in this case, it says 1-to-1, meaning that for every sample vector at the input, you put in this box, recurrent neural network. It has its own hidden recurrent layer, and you have corresponding one vector. So it's a mapping, similar to feed-forward neural network, except now this has a recurrent structure to it, which has a feedback. And there's another form where you have this input here, which is represented by some vector at t, and it's going to give you a sequence at the output. So 1-to-many. You also have many-to-one. You have a sequence, which is like a sentence, and it's going to give you one output, which is a class. Okay? You have another case where you have a sequence to a sequence, which is used often in translation. And you have another form of the many-to-many, which is a sequence to a sequence. The difference between this and this guy has a richer intermediate structure, which is the hidden units, which includes the state. So let's walk through the naming here. So this is, they say this is often targets applications in image captioning. So you have a single image, and you want to have a sentence output which tells you what's in that image. So this is a big application that big companies, Google and what have you, they use. When you have an image, they want to have a caption that describes what's in that image, or tagging, or things of that sort. This other one could be in sentiment classification, where you have review on Netflix. People write reviews of certain textbooks. Certain movies or what have you, the videos. So it's a write-up, which is a paragraph would be represented by a sequence, which is sentences. And this sequence is going to correspond to one output, which could be a class, saying this review is good or bad, for example. And then this one, when you have machine translation, so you have one language to another language, English to Chinese. Google has reported, I think a year ago, a system for translations called Google Translate, which uses these embedded recurrent neural networks to render translations among many languages. And one of the demos has been for example, Chinese and English, viewed as one of the difficult translations. And this is also could be for video classification. You have a sequence of frame, you have classification of this, or again, it's a translation. This shows us just some of the things that people have reported, applications. So sequence processing of fixed input. So you have an image, and then you want to grab something from that image, and you, for example, in this case, they're demoing a result of an application of a recurrent neural network, whereby they can read what's in that image. So they just grab things and they output here what the network eventually learns. This is just to motivate you. There's some successful applications, and these are just the past 3 years, people have demos like that, and they chose this as an example. Another example of a demo when you generate an image, which you write. So this is draws. As you can see here, you have nothing in the image, and then draws images, and it puts them sequentially one another. So this is a result of an application of recurrent neural network. So what is recurrent neural network? The so-called simple recurrent neural network. So you have an input, let's call it X. That input could be a vector of any dimension, and it's an instant T. And you have a recurrent block, which includes implicitly the state or the hidden unit. And then you could also have another part which is associated with the output. So the output vector, which it depends on the application. This output vector, it depends on the application. It could be a prediction. If you are trying to finish a sentence, you give the network some word and you want it to give the next word, or give it a character, you want it to give it the next character. So a prediction, or some of the applications we mentioned, translation, what have you. So what is the basic model? So the basic model differs from feed-forward neural network, is that now you have the input, which is the state, but also you have a hidden or version or a hidden unit or a state of the system. So the mapping now takes the input, takes the state or hidden unit at the previous time step, and gives you the present state. So the present state depends on its previous state, that's where the recurrency is, and also the input. If we didn't have this previous state, that becomes a feed forward. You just have an input going to an output. But this is what has recurrency. And the indexing here, the indexing is chosen here to be, you're looking at the current state, new state, at time t, and it's going to be a function of the input x at time t, and the state at the previous time. Okay? So, and you can view it when you have this mapping, you're going to have the same function and the same weights or the parameters. We have weights here, but you could also have biases. So imagine that you have the same one layer feed-forward neural network, and now you add another term, which is the previous state. That's what it is. Specifically, when you look at the so-called simple recurrent neural network, I'm not going to say the word here. It's simple recurrent neural network. So this is some graduate students started this process and picked up and became, at Stanford and others, they refer to as vanilla recurrent neural network. So this mapping is expressed specifically in this form. So here is an equation for the hidden units, the green. H represents, in this case, a state or a hidden unit. And it depends on the previous state with some weighting, and the input with its own weight. And they label the weights here so you know which weight it is. So this weight that maps x to h, this h, the previous to the present h, and then also you have an output which takes the state and add it here. Of course, you could add a bias here, and you could add a bias here to have the mathematical expression we've had before. So the bias is always good when the data perhaps doesn't have zero mean. So you need that bias to compensate for where the origin is. If you have any questions at any of these points, I'm starting very slow. I want to make sure all of us move together with this. Please bring it up. So a sample Mickey Mouse cartoon example is that if you say, suppose I want to train a network on the sequence hello. So first on the sequence hello, you say, okay, what are the distinct letters here? So you create the vocabulary, which is HELO. These are the unique vocabulary. So that becomes your vocabulary set. And then you want to train it on this to learn this hello, or in fact, you want to learn it to predict. So you want to do a character level language modeling. And these people, when they first developed this one here, this example, they came from language modeling and natural language processing. So the example is, in this particular case, you view this word hello as a sequence of characters, okay, and the goal here is to see if you can predict the next character for this particular application, just a demo. So first order of business, you're writing this input sequence, so you're not inputting the whole thing, you're inputting HELL. So you have a sequence of length 4 in this case, that's by choice. Okay, you could have chosen the whole thing, but said the sequence I'm going to train it for is of length 4. Step 1 is you encode the characters. So that's a step that you're going to see in a code that we're going to see in a little while. So this is a simple representation, often referred to as the 1 to k vector representation or the one hot element representation. So what is that representation? So it says that H is my first element in my vocabulary. I'm going to represent it. I have 4 elements in the vocabulary, so I'm going to take a vector of dimension 4. I'm going to have 1 in the position, the first position, to represent H, and the rest are 0. And this 1 is the position 2, which is the indexing of E to represent E, and this one is here for L, right? So this is just encoding. This has been the practice, how you encode these things. This is a choice of encoding, just to make things simple, that every vector is really far away from every other vector. Okay, in fact, every vector is orthogonal to every other vector. And then you say, okay, I'm going to have this model. I'm going to initiate the weights randomly, and for some random initial position, when I supply the sequence encoded as such, and I apply it to this mapping with initial random weights, perhaps the H's I'm going to get are going to be like that. That's just an example, okay, initially. And then you map the next thing, which is the output layer. You apply this random weight, and you get output at the end. So you apply this input sequence, and that's the output. And for this particular application, they're saying, I'm going to specify the target. I'm going to do a supervised learning. I'm going to specify the target to be as such. So what does that mean? They're saying, if you have an H here, I want the first output to be the next character, which is E. And if I want to hear, that's the desire. So this is what you desire. Of course, these characters have a representation like this encoding technique as well. And what do you do then? You just want to compare the desired with the actual output, and then you crank out the gradient descent. You want to minimize that error, and that's how you do the training. So if you apply a gradient descent. So obviously you have to define what your loss function is. Are you going to have an L2 norm, or you're going to have the Kullback liberal, or any of those other loss functions. And then for that loss function, you want to crank out the gradient descent, and that is the rule that you're going to apply to update the weights, incrementally update the weights. Okay? So this particular example says, I want it when I supply a sequence, you finish up, you predict the next character of that sequence. That's the goal of this training. Okay? And this person, I think in 2015, I believe, has a code that's written purely in Python. And it's this whole, by the way, handout, I just uploaded it. Unfortunately, I uploaded it this morning. So he has a code that actually implements for any generic simple feed-forward neural network. And it's efficient to the point that he has only 112 lines of Python. And he's proud of it, that it's very efficient that way, and it only has 112, and rightly so. And it's been a good example. And we thought we could actually start with this as a case study, so you can really get your hands wet with this example. You can extend it and what have you. And so it is this the location. I'm going to have a copy of this one uploaded to GitLab or D2L as well. Okay, so you have a .py file. So the rest is studying this example. So I'm going to leave this one now, because this is an implementation of a simple structure, flexible neural network of any size that you can program, and also includes the gradient descent, one form of gradient descent. So I'm going to postpone to studying this one here. I'm going to dwell more on the formulation and the mathematical expression. So I'm going to get out of this. Oops. And then I see if I can have oops. Oh, okay, so I think I got rid of that somehow. So simple recurrent neural networks. So let's repeat the discussion. What we started just a warm up to say blocks. Now we want to get into the nitty gritty and see what the model is and what it entails. So here just some description about the value of feedback and recurrency in making sure that it adds some richness to the capability of the model. And we will be talking about the learning technique, which is the so-called backpropagation. Now we're going to qualify it and say backpropagation through time. So there's a wrinkle of change of the original gradient descent that we talked about that makes it suitable for recurrent neural networks. Okay? So here's the same model we talked about. So I've tried to use symbolism here that's maybe more current in a way. So this notation in the literature now, we could say that the hidden units is here. This is sigma nonlinearity. This is an intermediate, the state. This is a matrix. Anything that's capital letter is a matrix. Anything that's small letter like B and C are vectors. So I'm writing the more generic general model of simple recurrent neural network. And so here is the input signal, S, the weight, plus the bias, which is this expression here. And then what you have here, U, brings in a feedback. So here's H, a delay generates H t minus 1. And you multiply it by this matrix, and that's the total sum, which is really, I view it as the state, then passes through nonlinearity, and that produces for us the so-called hidden unit. So I'm expressing X intermediate value as the state. So I'm having everything similar to feed-forward neural network in the sense that I have a linear mapping here. This is all linear, and I split the linear from the nonlinear part. So I only have the nonlinear part takes this signal, which I'm labeling as a state, and produces for me the hidden unit. And then the hidden unit maps through a matrix V, like here, plus a bias for more universal form, brings you the output. Of course, you could have another layer that converts this output into a softmax. So the output becomes a probability representation, which we know, right? So this is another similar thing. So you could have this output actually produces for us some P sub t, which is a vector of all of these guys represent probabilities. Any questions? So that's the model. And to be able to derive the update law, the gradient descent, we want to, typically the tradition here, you don't have to do this, but traditionally in the literature, what people do, they take this model, which is a function of time t, and they unfold it over time. So they just stepping every time and they unfold it. Look at what happens to the model. So what I've shown you here, that practice that is almost like tradition. This is the recurrent model. You unfold it by looking at every time step, and I'm showing you here at time step t, t minus 1 and t plus 1, and showing you here that every time step, you could view the time here as a layer. So in the time now, you view the time as happening in that layer. And when you view it this way, for every one of these layers, number one, you observe they're identical because we're dealing with the same C throughout, the same matrices. So that differentiates it from feed-forward network by having layers that have the same weights throughout when you unfold it. So that's, and the second thing, you have this, you have input to output, and you also have a processing between the hidden units. So the hidden units at the previous time is driving the hidden units at this time. So that's the wrinkle. That's how you take a recurrent neural network over some duration of time, and when you unfold it, you can say, aha, this now looks like a feed-forward neural network, where every layer now is really that time instant that you have. So instead of we're using the word T, the letter T here for time, but you could view it as a stage or an index. And actually, if you view it as a layer, then you can apply the same learning technique. So if I have a sequence of input here, it's going to produce a sequence of outputs. And then for any instant of time, I want this output to correspond to some value. So I'm going to, for every instant of time, I'm going to have a desired value associated with it. Then I take the discrepancy between the desired and the output, and they create a loss function, L2 norm or other forms, and then I can derive the gradient descent by minimizing that loss function, the same form. So that's one form of doing it. Of course, you have other forms where you don't really do that, and you just go directly with dynamic system and recurrent neural network and apply some optimization technique under constraints. And the result will be equivalent. So if you unfold it, you get this approximate model. Of course, when we are looking at feed-forward neural network now, we restrict the length of the sequence. We say the sequence is of this length. So when we talk about a sentence, we say it has this many words or these many characters. So you have to define the length of the sequence in this case. Okay. So if that's the case, so at this point, I said I have the sequence of outputs, and I have correspondingly desired values. And if I want to apply the L2 norm, I can take the difference between these guys, square them, and sum them, right? And then I have a loss at every instant, and then if I add them all together, I have a total loss function, which is really the sum of all the instant loss functions. If I divide them by the number of steps, it's like an averaging. Take an average of this loss function, which is my total L. Once I define this loss function, and I'm giving you an example here of my loss function LT for every instant could be the L2 norm, or as it is more popular, we can take it to be the cross entropy loss function for every instant. Then you sum over all the times and you have a total loss. Once I have the loss function, I'm basically done. I go to gradient descent. I just crank out these derivatives for every parameter, and I'm shooting for estimating this change of weight. So that would be the change of weight. This change of weight is going to have the sum. So the sum, which is the contribution at every instant. And by the way, remember that if we take a sum, it's the same as the average, because you divide it by 1 over n, and then you have an eta which you're going to select, so you can take this 1 over n as part of the eta as well. Right? So summing is really averaging. Every time you do a summing, it's like you're taking the average of these data. Okay? So that's called backpropagation through time. And it's a technique that extends the basic backpropagation for feed-forward neural networks or convolutional neural networks, okay, to the case where you have recurrency. We can obtain similar things in backpropagation. So remember that gradient descent, if we crank out the computation, we simplify that computation, we can generate this backpropagating network to simplify the final expression for the gradient descent. So you can have a feed-forward network which you start at initial time, let's say 0. Let's say you go for duration of from 0 to n. That's the number of steps, length of the sequence. So you go forward, you produce an output, And for every instant output, you want to take, for example, I've selected the difference here. I'm taking the L2 norm. And this difference for every t. Then for every difference, you go until the end of the sequence, which is, let's say, equal to n, I'm sorry. Then on this side, you have the backpropagating network. So you start with the end of the sequence at time n. You have this error, you generate delta n, and then you begin from some time, n minus 1, and you move all the way back to, if this is 0, this becomes 1. You move all the way one step before the beginning. Okay? This generates a sequence over time, or over time is like layers now for us, of the errors. What do we get from these backpropagating error? We get a transformation of the error called delta. You have the En, and you have delta that's defined for every t. So you have a sequence of deltas. Okay? In feed-forward neural network, we have a sequence over the layers. Now we have sequence over time. That distinguishes this one for feed-forward network. Feed-forward network, we're free to select the weights on every layer to be different. This one here, the analogy is that it's identical sequence in this case. And of course, what I'm showing you here, I'm just playing with the math expression to make sure instead of having this expression, you could write it in whichever way that would be convenient for you. In fact, my favorite is this last form where I split the equation to make it analogous to the form I have here, because I favor to have split the network to be a linear part and nonlinear part. And here I have a similar thing where I have backpropagating with this, what I call state or a co-state, and then the co-state presents this delta. So the bottom line, you have the sequence, you generate the errors over time, and then you have a sequence of deltas. That's how you generate the sequence. You have a sequence of input that gives you a sequence of outputs, that gives you a sequence of errors, and this sequence of error generates a sequence of those deltas. Okay? And then the update law becomes identical to the form we've had before for recurrent neural network, feed-forward neural network, which is an outer product of two vectors. For the output layer, the change in what we call it V and C, the matrix and the bias, is going to be an outer product of the actual error at every instant of time with the transpose of the hidden unit vector. And because we do this over all the time, we're summing here, we're taking the average. We're summing the contribution, and we have to adjust this hyperparameter eta. Okay? You do the same thing for this one here. So if you look back at feed-forward neural gradient descent for feed-forward, you're going to get the same form, except now instead of t, this t refers to the layer. Now this t refers to the instant of time. So here is for the output layer updates. They depend only on the actual error at that instant. Here's the update for the hidden layer, the recurrent layer, which instead of depending on the actual error, depends on the transform error we call delta. And you sum it over all the sequence length. So t is like whatever, from 0 to n, that's the sequence length. You sum the contributions here, and that gives you the change for the gradient descent. And of course, this eta here is some generic eta, could be fixed or changing depending on the applications. But it's identical form. Okay? So before we used to sum over the layers, now we sum over the time. Okay? And here, this is for bookkeeping for review. It just shows you how the gradient is computed. So what I've shown you is this. The expression for this derivative that we're trying to compute is of this form. Okay? And based on your expression, if this L is L2, then we end up with this expression. So here's the model that we are looking at, the simple RNN model. And I'm just showing you here more details, bookkeeping for more detailed information about how the calculus, vector calculus, is executed to obtain these expressions. So that's what you want to get a derivative of. You can do the computation element-wise, or you can do it in this vector calculus, gives you the final form. Okay? And the hidden units has this, you're computing this, which you break it down into, by the chain rule, into those guys, and these guys will contribute these terms. And this delta is defined to be this expression, and I'm just showing you that all these different expressions, they all are consistent with vector calculus. How to obtain the vector calculus? You either know about vector calculus, take a derivative of matrices and vectors, or you can apply the derivative element-wise and then bookkeep everything, collect everything, and put it in the appropriate matrix form. Okay? So here they're just details of how these vector calculus computations are. Any questions? Any questions? So what I want from this one is the form of the update is an outer product between two vectors, like in the gradient descent. This is a form that we can look at, is that I have in the update, I have a sequence that comes in, drives this forward path, and then generates errors at every instant of time. And then I generate the backpropagating sequence by this one here. So this is the backpropagating through time form. Okay? And these expressions are what the code implements. So when we get to the code, you're going to see things of this form implemented in the derivation. Okay? Any questions?
So how often are you updating the weights? Do you have to you have an input point and you
Yes.
go through that whole input and then after
So that's one instant. Well, that's one sample, right?
And
the whole input sequence is a sample.
And then after that sample, then you go back and update all the weights based off the collective error from that sample.
Well, you can do the update for every sample, or you can have a mini batch of samples. Okay. So now we're going to view a sequence as just a sample. Before we used to have a vector, right, as a sample. Now a whole sequence is a sample. You apply the sequence, do your bookkeeping, collect all these update, the change of weights. Are you going to update the weights at that sample, or are you going to have a bunch of samples like we've done before in the mini batch? Okay? So do you want the learning to be associated with one sample, or you want to do the learning or the change of the weights over a multiplicity of samples, which we call mini batches? Both apply. Very good. Any other questions? Because my intention right now is to go back to that code and try to dissect it and simplify it so you can feel comfortable with understanding what the code does. And it's only written in Python. You only need NumPy for it, nothing else. Okay? However, in the library, Keras library, there's an analogous code similar to this one here that's written in Keras. Okay? So we have two forms. Any questions? Ready to go to the code? Okay. So let me stop this guy or go back to the, yeah, here it is. So I think I'm going to, okay. So initially, here's the code. Just, okay, so he has the code on this side, and he's taking one part of the code at a time to introduce the components of the code. So the upper part here is just reading the data. So data IO. You only import NumPy as NP. And this part, you have a text in some called input text. For example, in the simulation that I'll share with you, I've selected, if I have it here, I selected this text. So this text says, in this chapter, we have this text. Okay, so that's my training in my example when I run it. But you have a text, and of course, it reads the data. It tells you how many independent characters in this data total, and then it sorts out independent characters. So what does that do? So you're reading the data. So data contains all the text, and then you set the data. It selects all the unique characters in this data, and you convert it to a list of characters. And this tells you the size of both, and then it prints that for you. And then here's the encoding. So this one from a character to an index. So it has a list, right? And it orders those lists, and each character is going to have a position in that list. So this is a transformation from the character you read to the position of the list, and vice versa. So this is just a transformation. This is the positioning an index, which is an integer, to the character. So and then the next part is initialization. So for example, in the choice here, hidden size, what's the size of the, in this case we call the state, the hidden units. We chose 100 hidden units. You could choose any number, obviously. The sequence length, he chose the sequence of 25. Learning rate is e to the minus 1. Is it okay to walk through this, or is it something, I know some of you maybe this is too simple, some of you. Should we walk through this or not? Is that okay? Yeah, because if you're too bored, I don't want you to, you can take a nap, okay, while we're doing this. How's that? So here you just define what the parameters are. So here are the matrices that he defines, and he has the biases, and the weights, he has them to be of the appropriate sizes. So that, for example, this weight that maps X to H is going to have the number of rows and columns, hidden size, which defines it here to be 100, by vocabulary size, which is depending on whatever you read, vocabulary size, whatever distinct characters. So it defines the dimensions of the matrix to initialize those things to be random. And the tradition has been to, for the bias, you just start them with 0. That's been the tradition. You only have the random small values for the matrices. This is the main body of the, so we start at the top and then we look at the bottom. And here we have some functions that we're going to come back to, some definition of functions. But really, this is the main body or the loop. So what does this do? It has indices, N and I. I'm sorry, N and P. P is for the data pointer. From the text, you're going to grab 25 characters at a time. Okay? And that tells you have characters here, you want to grab 25. And next 25, you get no overlapping. You just have it in this definition. So you use P for that indexing. Yes?
Is there any chance you can blow it up, or we can turn off the lights? It's a little hard to see.
Yeah, very good. I'm glad you said that. So let's see if I could do an improvement here and see if that happens. Can we turn off the lights here, or how can we, how is that?
That's better.
Is that better?
Yeah, that's good. Thank you.
Okay, very good. Thank you very much for letting me know. Yes?
That he chose, the hyperparameter, he chose 25. Right?
Yeah,
so
this,
you
could choose any number of,
right,
the sequence length. Yeah, very good. He chose 25 in this code, but you could change it. Yeah. So here you have two indices, n and I. N will be for the number of iterations, and P just when you grab 25 characters from the text that you have. Because you're going to partition your characters. You're going to 25, then the next 25, the next 25, till you pass through the whole sequence, the whole paragraph. And that will be one epoch. We call that an epoch when you pass through the whole thing, right? So this is the index. So it creates temporary memory locations, same size as the weights and the biases. And he defines an initial loss function called a smooth loss. He doesn't know where to start, so he just says, I'm going to define this initial loss function to be something that's proportional to the inverse of the vocabulary size. Vocabulary size will be distinct characters in the paragraph, 1 over, with a negative sign, so that will be a number that increases as the vocabulary size increases. And you multiply it by the sequence length. So you multiply it by 25 in this case. And here's the code. You say prepare inputs. We're sweeping from left to right in steps of sequence length. Right? So first you say if P plus the sequence plus 1 is greater than the data, that means you reach the end of the data. Or if the number of iterations is equal to 0, you want to reset. If you reach the end of the data, you want to reset this state, h previous, h of t minus 1. You want to set it to 0. Okay? So if you finish the whole epoch, you want to reset the initial condition of the dynamic system, which is the state. Then you start from p equal to 0. You go with the start from the data. So if you reach the end of the data, you start and initialize p equal to 0. And then you grab an input, which is, you take the data and you grab something from p and p plus sequence length, right? And what you grab will be characters, and you want to have the indexing from a character to an integer, which is the indexing transformation. So you check for every character, you look at its position in the vocabulary, and you get that digit. So here, the input sequence converted to a sequence of integers, where the integers will be the position of the vocabulary, the position of the character vocabulary, right? So actually, that's what we're looking at, yeah. And what is the target? What's the desired value? The desired value is just one character shift from wherever you grab. So if you grab this sequence, you want to also get one character shift of that. And again, you convert the characters into integers, which is the position of the sequence. So now you have a sequence of integers, right? And targets, which are shifted version of that sequence from the data, right?
Because we want the target or the output to be the next character in the
Exactly. So that's why they take this one. They say, I want this neural network to learn, if I give it one character, to predict the next character. Very good. And so that's one. So let's see. Then if you go through this process, right, until you finish one epoch, if you reach the end, you just start from the beginning and you can continue it, right? So it also, every time this index, this iteration, every time you do 100 iterations of this process, you do what's called sampling. And the sampling here is really like testing. Because what do you do in the sampling? The sampling, the sample is going to be, you're going to call a function called sample. This function is going to, it requires the initial state, H previous. From the input signal, it requires only the first character at that instant. So the input is like 25 characters, whatever you grab. And it takes the first character, and it's going to generate a sequence from that first character of length 200. So from that one character, you want to generate a sequence. So that's a function called sample. It requires this one here and generates for you a sequence from that one character. We'll see that sample function later, but basically intuitively what it does, your network, you give it one element, okay, which is from the input, and the output for that element is going to have an output, okay, and then you want to select the output to be like the next character. Whatever you get there with a high probability, you feed it in as the next input, and then they produce the next, and then so on. So you only need to test or sample this model, you only need one character from the input, and it's going to generate for you a sequence. And you continue by choice here for 200 sequence. Okay? Because remember, this is a recurrent neural network, so all you need is just you give it the initial condition, which is the H previous, and you give it the first input instant, and it's going to give you the first output instant, and presumably that first output instant, if it really learned, would be the next input. So you take the first output you get, you plug it in as the next sample input, gives you the next output, you plug it in, and so on. Then you generate a sequence, only from a single sample input, single character, and a previous state. Okay? We'll look at the detail of that particular function later, called sample. But view the sample now, because in the sample domain, the weights are fixed, frozen. So it really serves as a testing as well. It's like, how well is it doing? How well did I learn? Okay?
From the previous state.
Yeah, so I mean, there's a training, and there's this sampling. The sampling serves as a testing mode. Okay? So what happens? So you do that sampling, and you see, and it prints also it prints the text. So it takes a sample IX, which is the index, and then converts the index into characters, and then prints out for you the characters. So you can see the text. And then here, there's the forward sequence length characters through the net and fetch gradients. So you're going to have a sequence of the input, go forward through the net, you generate the backpropagating, and then you get the gradients of the weights for every one of those. So there's a function called loss fun, which upstairs we can talk about it later. But this function, it takes the input, the full input sequence, okay? It takes the target for that sequence, which you gave it, and it takes the previous H, because this is a dynamic system, recurrent neural network, we need some initial state, which is H previous, and it generates for us, goes through the backpropagation, calculates all this stuff, and generates for us the changes of all the weights and the parameters. We have them here. It also computes the loss function that you're using. What's the loss at that point? And also generates the final state, which we call it the previous, H previous. So it has from H previous of one input and produces the H previous for the next sequence that you're going to run. Remember, we view the whole sequence just a sample. I apply the whole sequence. I get the weights due to those sequence like we calculated in the mathematics, right? And that process needs an H previous to begin the process, and it's going to produce the final H, which will be the previous for the next sample. Okay? So that's why you have in this function H previous on both sides. But they mean different things. This is the H previous that helps you run this sample, and this output H previous is the one that will be H previous for the next sample that you're going to run. Okay? And it adds here a smoothing, smooth loss, the loss that you obtain here from that sample, loss of that sample, which is the whole sequence, is going to be added here, multiplied by a small, very small number, added to this H loss. So this equation here is really a low-pass filter. This serves to smooth the loss, because for every instant you randomly select those things, the loss could be up and down. It doesn't mean there's going to be, for every sample is going to decrease. It will be decreased over multiplicity of those samples. So this trick here is to compute the instantaneous loss for the sequence and then use it through a low-pass filter, contribute to the smooth loss. The smooth loss is one that's like filtered loss. So the big, humongous changes that happen to the loss from one sample sequence to another sample sequence are filtered out through this low-pass filter. Okay? So it keeps record only of the smooth loss. Right. Okay? And then the smooth loss, and then every 100 iterations, okay, which is here, it has n divided by modulo 100 equal to 0. Every multiplicity of 100 iterations, you're going to print the iterations and the loss value. So you're printing the loss, which is called the smooth loss, every 100 iterations. So what you see printed out will be the smooth, and also it's not the everything, it's every 100 iterations. Okay? And then here it says, once you have the change of the weights, and you have the smooth, and you have the change of you take those change of weights for that sample, and here you zip them together, so you have all the parameters parameters called parameters, which refers to any of those things. The program is very efficient. It's a good case study for you to see how it's done. And then the change in the parameter, this whole thing becomes change of parameter. And this mem is going to be memory location, the intermediate position that has the same size of the weights. Okay? So you define these parameters, and then what you do, this mem is defined to be, which is the same size, is going to be a pointwise multiplication of the change. So for every change of the parameter, you square it. That's just squaring all the change of the parameters, right? And then you update any one of those parameters by using the learning rate, the change in the parameter, divided by the square root of the mem, which is the square of the change of the parameters. You add some number, so in case this mem equal to 0, you avoid 0. And that is the technique that's referred to as Adagrad update. So it's a modification of the classical stochastic gradient descent by adding or dividing by the variance, which is of the gradient itself. Okay? And that's it. That's the core of the program.
So mem is what again?
Just a temporary memory.
Okay.
So they have a mem is just a temporary things, and they define it here to be the square of the change in the parameters. Because this is a pointwise multiplication, right? So every change of parameter is going to be squared, which really acts like, and then you take the square root, which is really the variance. So it's the variance of the gradient, which really tells you what's the measure of strength or power of that gradient. So you use that, you divide by it. Why? Because you don't want to use an eta that's fixed. So the effective eta for this one here, whatever eta that you use, learning rate, divided by the square of this mem. So that's the effective variable eta. So the way they have the variable eta here is that they divide it by the variance of the gradient, which means if the gradient vector gives you a large variance, okay, it says, I'm going to update slowly, okay? And if it's small, you want to increase that contribution. And then you just keep repeating that. So the idea in our mind here is that if you give me a sequence, right, I'm going to select the length of that sequence. I'm going to go sequentially through the sequence, non-overlapping sequence till the end, and keep repeating that process. And every time I'll generate the change of weights, and I do the update of weights, and every 100, so every 100 here I do the sampling. So note that every 100 iterations, you do the sampling. Every 100 iterations, you do the printing. So you print what the smooth loss is, and then you just show what the output for that performance. Any questions?
Should this sequence number that we choose, should it, so it's non-overlapping when it takes each?
Yeah, you just take sequence non-overlapping.
So if it gets to the end and there's only 15, but we chose 25.
Yeah, so at the end is just 15, then it says here, that's what you do, right? You do in the while true. So if the sequence, so you add the next thing, and it's bigger than the, right? So if it's bigger, then you just go and initialize it. So it says, so you have a, right? So if P plus the sequence length plus 1 is bigger than you exceed the data, you just set P equals 0. That means you start from the beginning again.
So there's a chance you could never go over the last part of the data. So about like 115 characters.
That's the way it is right now. Yes, absolutely. So if it's not divisible by 25, you can have a chunk of the data at the end. You don't. In this case.
Yeah, but that's just implementation. Yeah.
Right. So keep in mind in this case here, I mean, here's a few changes I can make, okay? One is that you don't have to make non-overlapping, right? So by non-overlapping, you're going to end up with some 15, right? Which you're going to drop at the end, right? But let's say I take one and I shift maybe one. Obviously, I'm going to get all the data, but I'm going to require more iterations. So it's a trade-off. So in this example, is saying, whatever, he feels by the end, he has already gotten the gist of that data. That's the motivation. But this is an option. So now we have two functions, which I think these are the key functions. So there's the loss function, which is a key function. So in the loss function, you just walk through the backpropagation technique. So there's the red part. So this is the loss function. So you give it the input sequence on the target, and you give it the previous H that you got from the last sample. And so you position this H previous that you got, you make a copy of it, and you put it at the end. You start with loss equal to 0 in this case, because you want to generate the loss function here. And then this is forward pass through the model. So if you walk through these things, this first step is to generate a vector with all zeros, and then the input, which is an integer, you're going to position a 1 in that position. So this is encoding of the character, of the sequence elements. Because remember, when you give it, it's just an integer, which is a position, right? So now you convert it to a vector of the same dimension as the vocabulary, which is variable depending on the text that you're dealing with. And then now, after you encode it, you just run through the model. If you look through these things here, just the model. And in fact, in this model, you have the output, and he adds another transformation of the output into a softmax. So the output becomes a probability. And then his loss, in this case, is the cross entropy. Okay? The cross entropy that targets, in this case, are either 0 or 1. Right? So you have the cross entropy expression here. And this cross entropy is added over all t. Okay? So that's the forward pass. And then the backward pass is you initialize the weights all zeros here, and then you do reverse, so you start from the end of the sequence. Let's say it's n, so you start from the last value, and you copy the output into a dy, which is, and then the dy you subtract 1 from it, so that's the difference between the output, which is output depending on how many characters will be values between 0 and 1 because of softmax. Each one of those will be between 0 and 1. However, the target is going to have all zeros except 1 in one position, right? So if you look at here, he subtracts, oops, I can't lose. So you define the error to be exactly the output. Then from that position where you have a 1, which is the target position, you subtract a 1. Okay? So now dy becomes the error. And then you update the weights in the final layer, which takes the error, exactly the mathematical model I showed you. This is the error, which is dy, dot with the transpose of the hidden units at the instant time, and you're summing obviously over the whole thing. This is the summation over all t of the sequence. And the change in B, the bias, is just the error. Okay? And then this is for the backpropagating. This expression is exactly the backpropagating, the so-called delta, which he calls a DH and DH raw. So DH is, in my mathematical expression, was like the lambda. Okay? DH raw is like the delta in the mathematical equation. And I want to show you that the connection between DH, which I call lambda, and DH raw, which is the delta, is this expression. And this expression here is the derivative of the sigmoidal function. 1 minus HS squared. this whole expression, just the derivative of nonlinearity. So that's lambda, derivative of nonlinearity, times to give you delta. Once you compute the delta, then the updates will depend of the biases will be equal to delta. And the other matrices that you have here will be the delta and the transpose of the input, the delta, the transpose of the previous value of H. And then you just, this expression is showing up here. So what you see here is exactly the mathematical model I showed you for the forward and the back propagation model. Okay? So he got it right. I checked this one and verified it. It's exactly that model. Okay? So actually he walks in details about this model. This is exactly showing you the mathematical model here. And then this is the backpropagating equation. The sample, if we look, what does the sampling do? The sample is going to needs a seed index, needs one index, which is a character, the first character, which is represented by an index here. So the way he defines the sampling technique, which is really the testing, is saying you sample a sequence of integers from the model. H is the memory state. So you define, here's the coding, you define the X to be the same dimension as vocabulary size, all zeros, and you place a 1. When you give me the seed, that would be the index of where I position the 1, because that becomes the encoding of that character. So I gave me a character, which is now represented by a vector of all zeros except 1 in the right position of where that character is. Then here's the processing of the sampling. It says, this is the model. So now we have an X, which is a single character. This single character is going to walk through the network. It's going to produce a probability vector in softmax. And so it's going to give me an output vector, each one with a probability of where the character is, because the characters are in sequence. And the highest probability would be that character. But on top of this, he used this function, which says you take a random choice. So you select an index using this probability, which is the output. Okay, so this function, random choice, is you have a vector and it gives you the output is telling you the probability of each one of these is such. Okay? And then this random choice could choose the top maximum probability or another probability. So I have which one of those is really chosen by this random choice, which says I'm going to choose one of these positions with this set of probabilities. It may select the top, it may not. Okay? So once you get that index, the index obviously there's encoded with the character, right? So every index corresponds to a character. Then says once you get the index, then you encode it. You just convert this index into a vector where this index tells you what that character is. And then you take and then you have the indices, just you have the sequence of indices. And you return the sequence of indices, which will be your sentence. And you're doing this process for n, which is, we chose it to be 200. Okay? So I understand walking through this one the first time is not, it's not very optimal, But we initiate the process. You have to sit down, follow these handouts, and try to look at that component. So initially, you begin with initialization, then you look at the main body of the program, then you have two functions. One is the loss function that generates the change of the weights and the loss, which you convert to a smooth loss. And the other one is the sampling, which is every 100 iterations, you're going to see what the performance is. Okay? And that's how the program is. Okay. So there are a lot of, this person pursued this approach for many things. One of these applications that he initially started with, he took all the writings of these several books of Shakespeare, textbook, used it to train a network with the aim of what? The network generates text that doesn't have to be identical to Shakespeare's textbook, but will be the same time. So the idea is to generate a text similar to, so you train it on the Shakespeare textbooks, and you want the network to generate something similar to Shakespeare's style. Okay? So he's shown you an example where he's beginning, and then you keep training, and then eventually you start producing things from the text that's similar. Okay? And he's shown you success stories of that application in some ways. He also discussed that he applied it to some very sophisticated things like geometry. So the idea what? The idea is to have a network that can look at a body of text of some type, and you train it on this body of text of that type, and you'd like the network to generate text that's obviously not identical, but similar to that type. That's the goal. And you can walk at your leisure through all these different things that he pursued in terms of what the text was and what the results was, and he claims interesting things. In generating C code, he tried to apply it to generating a C code by train it on a C code, and then see if the network can generate a C code. And so things that they did for fun, and you can walk through some of these things. Obviously, not every of these things is successful. Some of it is just like of interest. So I'm going to stop at this point because we don't have much time, and I'm going to see if I have, yes, I do have the code here. So that's the code that I actually ran, the same code I just copied from the link website. And I have a text, and I showed you what the text was. So that's the text I trained it on. And now every 100 iterations, it spits out for me 200 characters. Keep in mind, the characters here, space is a character, point is a character, everything, every character. So if you see it here, number one, you look at what's the iteration. I've been having it running before I came here. So this is the number of iterations, and this is now the loss. It starts with a huge loss at the beginning, and now eventually, this is the smooth loss, the average loss, and you see the smooth loss is decreasing. It may go up and down at some point, but eventually decrease. And you see, if I stop it at this point, I say, okay, let's stop it, see what happens here. And let's see the last text that it sampled out. So it starts from I guess, space. I'm assuming. Let's see the one before it. Maybe it didn't have space. I guess. So I'm not sure if that's space or whatever. So this is actually the text let's read one of these. So it starts with something, then th, perhaps the end of something, and then an accuracy over 96% without human intervention. Furthermore, in later chapters, we will develop ideas which can improve accuracy to over 99%. In fact, the best commercial neural da-da-da. Okay? So it has, apparently, in this case, it has a text that is very similar. So if you leave it overtrained, so it produces some of the stuff, and because in the sampling I have this initialization or the random choice, depending on how you set the random choice, if it has an n and this n appears in various positions, right? You have different options. I'll select what the next thing is, and it just runs with that, generates it. Okay. So this is a character level. So if you, so this one here, the vocabulary is just looking at distinct characters and define those distinct characters. You could insert a statement here where you split the set into words, just split it into words. The only disadvantage there is that obviously it's going to have more size of set. Set will be larger size than if you just limit yourself to a character. The English language, whatever, will be something, the characters plus other things will be finite, but if you have words, you have a bigger set, and if you have a bigger set, the way it's set here, that the dimension of the vector is the same size of the set. So that's a trade-off that you could consider. But of course, if the text itself is limited, so here's an example where I can insert this thing here, this statement. I've inserted this statement. This statement, now I'm training this text. It's the word level kind of training. So in other words, word and the next word, as opposed to what we did before, which is character level. So character level, you take also the space. So if you take this one here with the word level, the dimensionalities obviously will be different. So let's see if this is, if I insert that, what happens? So it starts word level. Now it actually prints a whole word. And I believe this is the word level, yep. So the advantage of this, so it starts like with large loss function, smooth loss function, but you see it decrease over time. And if you let it, then you see the result, okay? So I'm gonna upload this code as well for you at D12 and also GitLab. And we're gonna stop at this point.
So line number 11 was the only change that you made?
I'm sorry?
Line number 11, the list set data?
In this case here, I believe that's the only thing I believe. I think I did this and I may actually add other things. But in this case, I'm just showing you an example where when I insert this thing here, I take data and define it as a set. No, is that right, or I'm not sure. I'm not sure I have it here. I think, let me see if I have it another way. No, I'm sorry. The command is here. I think that's the command I didn't do it here.
No,
the command is data split. Okay, so when you have data split, it's going to split it into the words that you have. Okay, so this one, yeah. This command, data split, splits your text into separate words. So it's not at character level, it's a word level. Okay?